Greetings, dear colleagues. My name is Valerii, and I'm glad to present our research on the topic improving the efficiency of damaged buildings detection based on ASPP technologies. The authors are Valerii Dymo, Aleksandr Gozhyj, and Irina Kalinina from Petro-Mogila Black Sea National University. Recent studies show the effectiveness of convolutional neural networks such as YOLO, ResNet, UNet in complex object recognition tests. But even modern models require more detailed research into their application in tasks like recognizing damage to buildings and surroundings, and reveal existing difficulties in detection objects of different sizes, shapes, their ages. To improve the efficiency of models, different training methods, functions, and metrics are used, as well as more complex architectures and processing algorithms. In our previous study, a classical UNet architecture model was built, originally developed by Olaf Ronenberg and others. As you can see on the image, the distinctive feature of the architecture is due to the implementation of two parts, contracting and expanding path. The model was used for semantic segmentation of damaged buildings. As a result, an overall accuracy of 84.21% was achieved, as well as corresponding intersection over union metric of 45.83% for damaged and 49.14% for undamaged buildings on the evaluation dataset. This study proposes the use of spatial pyramid pooling to potentially improve the model by applying multiple pooling layers with different distance rates, which allows selecting the required feature of objects in the image at different levels of scalability. Using the ASPP model instead of bottleneck will reduce the computational complexity of the network and improve image segmentation using heterogeneous convolutions, the example of which you can see on the picture below. The general architecture of UNet remains unchanged, but the conventional bottleneck is replaced by ASPP. In the image below, you can see that the model consists of 1x1 convolutional layer, followed by 3 convolutional layers using heterogeneous convolutions with different distances, and a pooling layer. After that, there is a concatenation and 1x1 convolutional layer. The dataset from the previous study has been doubled. The data includes 100 Google Earth images of the city of Mariupol taken in 2022. Various augmentations such as shifting, rotation, and scaling were also added to the set, and weight maps were generated to balance the number of pixels. Thus, the set consisted of a set of original images, segmentation maps, and weight maps used in the training process. Categorical cross-entropy was chosen as a loss function, which calculates the distance between the actual class distribution and the corresponding prediction. And also intersection over union was used for calculating the accuracy of the model, which takes into account the intersection between the predicted image and the ground truth. About training process. The model was trained on NVIDIA T4 GPU using Google Colab service. Training was performed on smaller images due to the memory limitation of the GPU, and appropriate augmentations were applied to the dataset, which increased the variability. 70% of dataset was divided for model training, 15% for evaluation, and the other as test images. You can see some training results of the initial model on the screen. So what are the results? As you can see, 4 main models with the best performance were selected, among them the base model and model 3, which has the second best performance, stand out. The model without ASPP was compared with the performance on the evaluation dataset, since the previous study assumed a simple partition. Despite the intersection over union performance for building classes is higher in the model without ASPP, the overall performance for the new architecture models is better, which means higher segmentation accuracy. There are still difficulties left. The basic model with ASPP has a lower value of losses on the evaluation dataset, as well as increased accuracy and average value of intersection over union by 5.39%. It is worth noting that Model 1 showed the best results among all models at 23rd epoch, 45.8 intersection over union for damaged buildings, 51.47 for intact buildings, and with 60.7% average intersection over union. The model still requires addressing other inequalities, such as confusing some objects or the inability to identify heavily destroyed objects from the rubble. The conclusions are next. The UNet model using ASPP as bottleneck was implemented for segmentation task. The dataset was expanded and voice augmentation were applied to increase their variability, as well as weighted maps to balance the existing classes in the dataset. Models with different parameters were built and compared. It was possible to achieve a reduction in losses and increase in the intersection over union metric by more than 5%. Difficulties in the segmentation of some images have been investigated, which require further research into the datasets, algorithms, and the architecture. The presentation is over. Thank you for your attention.